Good afternoon. I'm sure you all know me. I'm Ian, and I wanted to start this talk by just throwing up a few photos of some of my pastimes. So I really like outdoor stuff. Cycling and mountaineering are my two main sort of hobbies, and I go out with my friends and my brothers, and basically try and get as far away from people as possible, and normally stay there in a tent. But there's something about these photos which to do with chemistry, which ties them all together, and it's to do with the gear that I'm using. And what ties it all together is the subject of this talk, which is PFAS. So these are fluoro polymer compounds. So the title of the talk is asking the question whether PFAS are a bigger environmental disaster than microplastics. We've all heard of microplastics. They're in the news all the time, polluting the oceans, getting ingested into sea creatures. But PFAS, maybe not something people have heard about so much. So I'll let you be the judge by the end of the talk and see what you think. So the structure of the talk is, I'll start out with a bit of an overview of what PFAS are, a bit about why they're useful and where we find them. Then I'll get into the details of why they're a big problem and what we can do to try and solve this problem. So first off, what are PFAS? Well, it stands for per and polyfluoroalkyl substances. So effectively what we're looking at is carbon backbone with fluorines on it. So it's very much like a hydrocarbon, but where you substituted some or multiple hydrogens for fluorines. And they can be polymers, like these here. So PTFE, very common, you're probably familiar with it. PVDF, for battery people, I'm sure they'll be familiar with that. PFA is another fairly used, particularly in labware. Or they can be non-polymers. So these two here, PFOA and PFOS, are both industrial surfactants. And then the one on the end, perfluorodecaline, is used in cosmetics and in surgery. It's really good at storing oxygen. So there's just a few here, and actually more than 4,700 different compounds exist and have been documented. Why do we want to make all these compounds? Well, they have a lot of really useful properties. Now, I'm not going to go through all of these properties, but to sum it up, they don't interact with the world very much, and they don't react with things that you put them in contact with, and they last a really long time doing whatever it is they do. So they don't degrade, and this gives rise to a lot of potential applications. So they are really found everywhere. So I'll take you through a few of these different objects that I've got on the screen. Start with disposable paper food packaging. So often it's coated with a layer of a PFA substance to basically give it a hydrophobic property and repel oil as well. And the same is true with non-stick pans. If they use a PTFE coating, that's a similar sort of property there. Then we've got other stuff as well, like fire extinguishers. Foam fire extinguishers often include a PFA substance because of their high resistance to heat. Then we've got Gore-Tex, you might be more familiar with. The membrane inside of waterproof jackets. It's a stretched form of PTFE, which gives it breathability, and also its waterproofness. And then, in addition, in a waterproof jacket, you have the surface material on top of the membrane, and then that's normally coated with a durable water repellent, which is another PFA, which often washes off. And then we've got things like lubricants for bicycle chains, include PTFE to get those components running really nicely. Climbing ropes, dry treated for water repellency. Batteries, I mentioned. The semiconductor industry uses a lot of fluoropolymers just because of the harsh conditions during lithography. Even in cosmetics, so waterproof mascara and makeup, that sort of thing. Often they use fluoropolymers to give that waterproofness. So yeah, they really are found everywhere, and actually more than 200 different use categories have been identified, and there's probably more than that. So we've got this huge range of different compounds with a huge range of different applications found throughout all of society. And yeah, they're even involved in our work. So if we're in fuel cells or electrolyzers, then naphthalene will be very familiar. The proton exchange membrane, so the advantage of using a fluoropolymer here is you're trying to conduct protons through a membrane, so it needs to be able to survive in really acidic, harsh conditions. And it also needs to be water repellent, so in a fuel cell you really want to get rid of that water. And then in batteries, PVDF is a standard binder, and basically because it's inert under the conditions inside the battery, doesn't react with the lithium or with the electrolyte. So very useful materials, but there is a bit of a problem. So let's play this little video. Okay, so that was quite dramatic, but it does highlight some of the points I've been talking about in terms of the prevalence of PFAS throughout the world. And it leads into the problems with PFAS. Now, firstly, this comes directly from one of the advantages to why you want to use them. So they are persistent in the environment, so that means effectively they are what's called forever chemicals, and that comes from the fact that they don't degrade, which is what we want in their application. That's not great when you're putting it into the world. And secondary to that is their bioaccumulative nature. So this means the substance is absorbed by living organisms, but it can't be broken down. So it's being accumulated faster than it is lost. So you end up with a buildup. And not only that, but in the food chain, you'll end up with those at the top of the food chain getting magnified effects of that bioaccumulation. So this all sounds a bit questionable, but what's particularly concerning is that we don't really understand the effects in terms of health and environment of these molecules. They're pretty much unregulated in their use, and no one's really studied it. And to make matters worse, the ones that have been studied, well, it's kind of bad news, as you'll see. So I'm going to take you through a little case of this particular PFA substance, PFOA, so perfluorooctonic acid. Now, it was one of the first PFAs that was developed during the Manhattan Project, actually, and then 3M produced it commercially in the States from 1947 until the early 2000s. Now, what is it for? Well, it is a surfactant molecule. So we have the fluorinated carbon backbone, very hydrophobic. Then you've got a carboxylic acid on the other end, which in its salt form is a really good hydrophilic head to it. And it's used in it was used in a lot of applications, but primarily in the production of fluoropolymers like PTFE. So PTFE, when you're doing the reaction to make it, it doesn't really dissolve in any organic solvents, so you have to do it in water. And then to aid that process, you use a surfactant. So you basically get little micelles formed in the solution with the PTFE particles growing inside. Then you get your PTFE, you wash out all the surfactant, and then you're left with a load of PFOA contaminated water. DuPont was the biggest customer for 3M because they make Teflon, which is their commercial version of PTFE. Now, they made headlines in the early 2000s thanks to the Robert Billet investigation. What was this investigation? Well, there was a farmer in West Virginia who had lost 200 cows.
How many did you lose?
190.
190 cows.
You tell me nothing's wrong here.
He thought that it could be something related to the DuPont plant that was nearby.
That's chemicals, I'm telling you.
I'm seeing documents I don't understand. They're hiding something.
PFOA is this unknown substance, unregulated, but he found that both DuPont and 3M knew they had been studying the effects of PFOA on lab animals and on their own employees. So they knew basically about 40 years prior that this stuff caused cancer and also led to high cholesterol. And they found that it had a particular severity in females.
What if you drank it?
Drank it? It's like saying, what if I swallowed a tire?
What if whatever's killing those cows is in the drinking water?
They kept this all quiet. They didn't tell anyone. And why? Because DuPont was making $1 billion a year in profit from their Teflon.
At DuPont, better living through chemistry. It's our DNA.
They didn't want to tell anyone. They wanted to keep on making Teflon. And in addition to that, DuPont, knowing these hazards, put their PFO waste in. They released the effluent into local waterways.
What in the hell's going on?
DuPont is knowingly poisoning 70,000 local residents for the last 40 years.
And this is what led to the death of the farmers' cows. And what they found was much elevated cases of cancers and whatnot in the local area.
You knew, still you did nothing.
This was a really high-profile case, and then a lot more science was done to look into the effects of PFOA, and they found that you can find PFOA all over the globe. Like they found in 99% of Americans in their blood. So basically that means everyone's got some in their blood in some level. And yeah, it can be found in pretty much all organisms on Earth. As part of the investigation, they got 70,000 volunteers from the area to give blood samples, where they were then studied and then correlated that with the diseases which they developed. And this kind of led into the established health effects of PFOA. Now, if you're more interested in this case, some of you may have seen these films already, but I can recommend both of these films. I've seen Dark Waters. It's on Netflix. Impact on human health. So this is taken straight from the EPA with regard to PFOA specifically. Now, I'm not going to go through all of that, but if we pick out the keywords, what they found was it leads to lower fertility problems, problems with pregnancy, developmental issues for children, babies, a whole host of different cancers, and problems with immune response and how vaccines are effective, and then cholesterol, higher cholesterol as well. So this was based on the 70,000 people who were exposed to much higher levels of PFOA than anywhere else in the world, really. But it kind of illustrates what happens if those levels get elevated. So this is all really bad. We have all of these different chemicals that are used all over the world, and they're probably quite bad, and they're in levels which we're going to keep going up. So what do we do about this? What do we do? Well, the latest thinking comes from this fellow Ian Cousins, who proposed the idea of essential use. And this was backed by 200 scientists, and it's designed around restricting the use of PFA substances and developing alternatives. Because clearly we can't just put an outright ban on these substances because they're so integral to a lot of functioning of society. So the idea is essential use. And what does that mean? Well, it comes from the Montreal Protocol and around surrounding CFCs. And what it states is that the substance must be necessary for health, safety, or critical for the functioning of society, and there must be no available technically and economically feasible alternatives. Okay, fair enough. So what does this mean? Well, we kind of get three categories. We have non-essentials. So these are applications for the PFA substances, which we can pretty much just say, we can't do them anymore, you're banned, get rid. And these would be things like where they're used in cosmetics, in PTFE-coated dental floss, for example, or in the food packaging. Then we have substitutable, and this is where we have a use case which is essential, but there are alternatives, they may be more expensive or not used for some particular reason, but we can substitute them in because that would be not PFA. And these might be like maybe in the case of the fire extinguishers or in waterproof jackets, and even in membranes for fuel cells, for example. There are hydrocarbon ones that are being worked on. And then lastly, we have essential, so the substances which fit the criteria previously described. And these would be things like in fireproof clothing, where there's nothing really else you can use, or to go back to naphthalene again, it's used in the chloralkali process, and it makes that process basically infinitely better than if you didn't use it. So, yeah, but there's a bit of a problem here. We're basically having to go through case by case and sort of assign it, and there's going to be an argument each way. Obviously, the people who make the PFAs want things to be essential, and you kind of end up with a bit of a spectrum. So it's a bit blurred, and it becomes a really big problem for legislation and regulation. Yeah, so in summary, PFAs, they're here to stay for a long time, and yeah, we have to do something about that. And I think starting with public awareness is good. You know, things like microplastics and stuff are really publicised about a lot, but this is less well known and could be a bigger issue. And then we really need regulation, so we need to just, yeah, crack down on the use of the chemicals and restrict it, and the work of scientists to look at alternatives and try and substitute things out. And I think it is a bit of an uphill battle, really, because of how established the use of these chemicals is in society. And I think that even in the essential use statement, I think that there's problems there. So the phrase economically feasible, I think, is basically just an excuse for companies to say, well, you know, we're going to stick with the PFA substance. So I think it is an uphill battle for regulators. But yeah, if you found the talk interesting, I can recommend some other reading, a couple of papers, and there's some good websites. But yeah, thank you very much for listening.